So good evening, students. So we have been now covering the approximate method. In the previous class, we introduced the Rayleigh's quotient, and then we saw some examples also in that. Till now, we are focusing on the fundamental natural frequency using the Rayleigh's quotient. Gradually, we'll see the this method can be used for the multi-degree of freedom natural frequency shapes we can able to get. So today we'll continue with the Rayleigh's quotient, but you'll see that a different form of the Rayleigh's quotient will be using it, and different forms of the Rayleigh's quotient will have different requirements of the functions which we choose. The comparison function, or we'll see that there is another function which is having less requirement, in which we require only the boundary condition of the geometrical type need to be satisfied. There is no need to satisfy the boundary conditions of the natural boundary conditions. So anyway, as we'll progress, we'll see those requirements. So today I will start with the Rayleigh's quotient in the different form, and then we'll see using the eigenvalue problem closed form solution, which were very difficult to solve to get the eigenvalue or to get the natural frequency. Here it will be relatively easier to get, but there will be some approximate values. They will not be the exact one, but as an engineering approximation, they will be close enough to use them. So I'll share the slide. So Rayleigh's energy form now we'll use. In the previous lecture, I used this energy form in the discrete case. In the discrete case, the advantage of this method is not that much came out, but now we'll see that for the continuous system, especially, this method will be more useful, because if you see this particular energy form of the for the discrete system, as such, in the previous case, in the Rayleigh's quotient case, without in the energy form, only we were multiplying the k into u and m into u, and we're getting the bonds, the enclosure, using the enclosure theorem. We were getting the we are enclosing the natural frequency of the system. But with the energy method, some more multiplication need to be done, and we are getting the natural frequency. But here the things are in the discrete system. We are not getting that much benefit of the method, but now in the case of the continuous system, we'll see the more advantage of this. So because the continuous system, different continuous systems are having different form of the energy, kinetic energy, potential energy. So this particular first thing I am taking as the axial vibration. So this is very important to note that which particular vibration of the one system we want to analyze. The same system, like cantilever case or any other case, we can have torsional vibration or axial vibration or the transverse vibration. Depending upon that, we have different L operator, M operator. So here, the axial vibration of the rod we are considering with the and which is also called longitudinal vibration of rod. So usually we take the solution in the form of separation of variable form, in which we assume the response as the function of the spatial coordinate and the temporal coordinate, where f is the harmonic function. So the kinetic energy expression for the axial vibration is this one. So if we substitute the solution, so we'll see that here differentiation is with respect to time. So the ft function will get the differentiation. So here f representing the time derivative of the f, and because the square is there, so f square is there. So within the integral, all the terms containing x, so ux, because is function of x, so is inside the integral, but ft is not function of x, so it has been taken out. Similarly, the potential energy, when we substitute this assumed solution, here this function of or differentiation is with respect to x, so the u will get differentiation. F will go out of the integral as it is with the square. Now here there is no derivative with respect to time or the x here. So this is the kinetic energy and potential energy, and the Rayleigh's quotient in the energy form we can write like this. So using this previous expression, this because for this we know is a simple harmonic. So when we use sine function or cosine function, the omega will come out from this. So that is the way we have defined the Rayleigh's quotient. So see, this is the energy, the potential energy. This is the kinetic energies, that is T star we wrote. So if we would like to compare this Rayleigh's quotient in the energy form with the previous expression which we discussed in the last class, in which we use the eigenvalue problem was the starting point. So if you see here, we are using U, L operator U, where L operator for the axial vibration is the double differentiation with respect to x. But if you see here, we have in the energy form, we have single differentiation with respect to x. So this is the main difference in the Rayleigh's quotient when we are using the eigenvalue problem formulation and using the energy. Here, this differentiation is having some meaning, because you can see that here the differentiation is one less, and actually both this form and this form are same. In fact, from here, if we substitute this L operator and M operator anyway will give the same thing. Here, if we do the integration by part of this and satisfy the boundary condition, then we'll see that we'll get the same expression. So we need to do the integration by part of this once with respect to x, and then this one of the derivative will come to the u, and another this will reduce, so we'll get the same expression. So they have one and actually both are same, but only the differentiations order is different in the present form. Here, as we know that the Rayleigh's quotient takes the minimum value when this function, if we are choosing, which is close to the first normal mode. If that is not close to that, then it will be giving the more than the first natural frequency. And here, because we are not solving eigenvalue problem directly, we are assuming this ux function. So here, we need to, so while choosing the ux function, the only requirement will be we need to satisfy the boundary condition of the problem. If it is cantilever beam or there is fixed beam, So accordingly, we need to satisfy the boundary condition of this of the functions. So through example, we'll see how we need to, while we'll be choosing this function and satisfying the boundary condition. Then I'm giving another derivation. So we'll take some example for this case. But before that, let us take the energy method if bending vibration is there. So we know for bending vibration, the kinetic energy expression is this. Potential energy expression is this, in which we have differentiation with respect to y double derivatives are there and the square of that. So if we assume the similar form of the solution, then this Rayleigh's quotient for the bending of beam case will reduce to this. Now, if you see here, we have the differentiation of the second order, and in the Rayleigh's quotient with the eigenvalue problem of this form, in which we started with the eigenvalue L operator and M operator, the L operator is having fourth order differentiation. So here there is order of differentiation is 2. So 2 less order we are having in the energy form. Again here, if we substitute this L operator here and do the integration by part with respect to x 2 times, this Rayleigh's quotient can be converted into this form. So they are representing one and same, but some more terms will come. They contain the boundary condition. So let us not expand that at present. So we'll take up this, and then we'll ensure that when we choose the UX, we need to satisfy all the boundary conditions of the problem, so that whatever the natural frequency we'll get from this will be consistent with the problem which we have in hand. So now I'll take up a few examples so that whatever the method I discuss will be clear. So here we have one, basically there is this rod I have shown, but there is a spring here, and spring is having distributed mass. So usually we don't consider the spring mass, but here is given that the spring is having mass per unit length ms, and apart from that there is a rigid disk at the free end of the spring. The mass of the disk is md, and is vibrating up and down as we generally consider for the spring. Total mass of the spring will be, because length of the spring is L, so total mass of the spring is ms. So now because the spring is a distributed system or continuous system having continuous variation of the mass, and the disk is there. So because spring can be idealized as a rod having axial vibration, so that's why this equivalence of that has been shown here, that this rod is having a stiffness K equivalent to the spring and is vibrating up and down. So here, if you remember, when we had the axial rod vibration with mass at the free end, the eigenvalue problem, when we formulated, it has the boundary condition containing the eigenvalue. So then we had difficulty in the frequency equation, and the frequency equation also had the transcendental form. So here we are not going for the solution using the eigenvalue formulation. Directly we'll be using the Rayleigh's quotient and obtaining the natural frequency. So here, because this is a spring, so let us say the free end of the spring, which is at a distance L from the support, is UL, the displacement of the this disk itself is UL, that is the maximum displacement which the spring is taking place. And if you want to predict the displacement of the spring in between, that will be given by ux by L into X, because the stiffness, the variation is the linear. So the displacement at any point on the spring will be ux, which will be given by this expression. If we take the derivative of this to get the velocity of the spring at any point, then if we take the derivative, because these are the constant, so this will be the velocity. X is the location. Sorry, I think this should be the. This should take X is the location, so that is not, derivative should be there in the U, not in the X. So we have this is the velocity of the spring at any point from the support at location X. Now we want to write the kinetic energy of the system because the Rayleigh's energy form requires that. So kinetic energy, the disk kinetic energy will be this much, because disk is having mass and the velocity UL dot. So this is the kinetic energy of the disk. Spring is having continuous variation of the mass. So this is the mass per unit length into the velocity square, and there is the distance, this is the length of the spring segment which we have taken. So this is the kinetic energy of small segment, and then if we integrate, we will get this kinetic energy of the whole spring. Now this mx is ms, that is a mass per unit length, that is uniform. For the present case is uniform spring is there, and the velocity we already obtained this at any location on the spring, so that can be substituted square of that. So this is the kinetic energy of the spring because it's having inertia, and this is the kinetic energy of the disk which is at the free end. If we integrate this, we will get the expression like this, and if we rearrange, we will get the kinetic energy of the system like this. So md plus md is the mass of the disk, capital ms is the total mass of the spring, small ms into L, so ms by 3 into ul dot square. So this is the kinetic energy, which if we want to write in the form of the harmonic form, then we can write the u dot as omega ul. So this will give us omega square. So omega square, the coefficient of that is nothing but the T star which we defined. So T star will be this much. Now the potential energy, because spring stiffness is given, so this will be just half K ul square, because the maximum extension of the spring is ul, so that much kinetic potential energy will be stored. Where for axial rod, this is the expression. For spring, we can have other expression for the so spring of the spring is given to us. So this is the spring will store this much potential energy. Now we write the Rayleigh's energy form. So the Rayleigh's is the potential energy. This is the T star which we obtained earlier. So if you take the square root of this, we will get K divided by M equivalent. So if you see here K, and this we are writing as M equivalent. So that is this expression is very familiar. This should be single equal to. This is very familiar for single spring mass system. When there is no mass of the spring, then we write K by M. But here we are getting K M equivalent. So M equivalent is MD plus 1/3 of the spring mass. So that means if we have the spring mass to be considered, then we can have one. We can idealize a spring mass system, spring having no mass, and the spring mass of 1/3 is attached to the disk. So here it has been shown that this is the spring having no mass, but we have added that particular equivalent mass of the spring to the disk here. So these two systems are having equivalent natural frequency. So that means if you want to consider the spring mass into this spring mass spring mass system in which the spring is having no mass. So you can see that just we need to add 1/3 of the mass of the spring to the disk, and that will give the natural frequency of the continuous system related with the this. So this is the one example how we could able to get the natural frequency quite easily using the this energy form of the Rayleigh's method. Another example I will take up for the bending of beam case. So for bending a beam, this is the rigid support. This is the beam is there. Beam is having one mass here. So in the continuous system, we have seen that for bending a beam case, we solved cantilever case or free fall case, and the expressions were bigger because it involved the eigenvalue problem involved the four coefficients, and now here you can see that the boundary condition will contain the eigenvalue. So here we will be having the boundary condition will be containing eigenvalue. So the satisfaction of the boundary conditions will be much more difficult when we have the disk here. But with this energy method, we can able to get the natural frequency like this. So here again, here m is the ms or m is the small m is the mass of the shaft per unit length. Capital M is the mass of the disk, MD, we should be taking. So here, what we are doing, the UX which we are choosing here is this is the actually in strength of material we obtain the deflection relationship. If there is a load, how the deflection of the beam will take place. So this is the same expression. So the deflection of beam relationship. So at any point onto the beam and in the axial direction, we can get the displacement of the beam using this. So this is the basically elastic line or relationship for a cantilever with a load at the tip for that case. And for beam deflection at free end using this relationship, or this anyway is the deflection of this. We know the relationship. This should be L cube or L cube. I think this should be okay. So this relationship, you know that the free end, the deflection will be UL, or will be given by like this. Now, if we take the velocity of this, so the derivative of this will be there like this. So this is the derivative. Here, again, the mass of the shaft is ms per unit length. If we multiply the mass of the length of the rod, so this will be the total mass of the shaft. So here now we are writing the kinetic energy of this system. So this is for the disk, because disk is there at the free end. So this is the kinetic energy of the disk. This is the kinetic energy of the shaft segment. So this is at velocity. This should be square, I think. Yeah, this should be square of this. Ms is the mass per unit length. Length of the segment is dx. This should be square, so that yeah. So this is the kinetic energy of the because here the mass of the shaft we are considering. So this is the kinetic energy for that. This is for disk. And now we can substitute the velocity from this in this expression. So we'll be having this term, and then we need to integrate this with respect to x and simplify. So if you simplify this, there is no change in the kinetic energy of this part. So we'll get something this 33 by 140 ms. Ms is the mass of the shaft, and md is the mass of the disk. So we have taken the ul dot square common. So now you can see similar to the previous one, because of the harmonic motion, we can able to write the ul dot as like this, and t star will be then this within the including the half. So now we got the kinetic energy. Potential energy will be the stiffness of the cantilever beam. K, we know this expression. So ul square. So this is the potential energy. So we use the Raleigh's energy method here. So this is the potential energy. This is the kinetic energy of the whole system. So this can be simplified, and if you take the square root of this, we will get the natural frequency of the system. So here you can see this is the stiffness of the spring uh, of the cantilever beam here, and this is the equivalent mass. So you can see the disk mass is there, and if you want to consider the mass of the shaft, so we need to, if we divide this, I think we'll get around 0.235 ms. So this much mass we need to add to the disk, and if we consider the shaft as massless, so that will give the same natural frequency as the continuous system. So this is some kind of equivalent system in which we lump the mass of the shaft to the disk by factor multiplying by 0.235. Then the new system having no mass of the shaft, only the disk having additional mass, will give the same natural frequency as the previous system. So now you can see, especially the fundamental natural frequency, how relatively easier we can able to find as compared to the eigenvalue problem in the closed form solution method. So this is another example which we can see the potential of these methods, approximate method. Now we'll take more complex beams. So here we are considering a tapered beam, taper rod. We want to analyze the axial vibration of this. The variation of this, because of that, the mass is varying like this. So along the length of the beam, the mass per unit length is changing like this. Even the EA, because cross section is changing, the distribution of the EA is given by this. So here the geometrical complexity of the beam is there. This is the cantilever case, cantilever, and in axial vibration we want to study. Now here in the energy form of the Raleigh's beam, we know that the whatever the comparison, whatever the u we need to choose, there is a comparison function, and comparison function is having requirement that it should satisfy all the boundary condition, not only at this end, the geometrical boundary condition, but also the natural boundary condition, which is nothing but the axial force should be 0 at the free end. Now, if we choose this as eigenfunction, x by L, x cubed by 3L cube. So if you see this, we'll check whether they satisfy the boundary condition. So for the x is equal to 0, this particular function, because x is 0, then it satisfies easily. There is no issue regarding the boundary condition at the fixed end. Automatically, if you put this x is equal to 0 at fixed and the ux becomes 0. So it is satisfying the boundary condition here. Boundary condition here requires the derivative of this. So if we take the derivative of this with respect to x, so we will get 1 by L, then x square by L cube. Now we'll satisfy the boundary condition at x is equal to L here. So if we put x is equal to L here, we'll see that this becomes 1 by L. This is L square by L cube, which is nothing but 1 by L. So this will get cancelled and we could able to satisfy the second boundary condition also with this comparison function. So now this comparison function is suitable for us, and it is now we can able to use the Rayleigh energy form directly. So Rayleigh's energy form for the axial rod case we derived like this, in which we had the single derivative of the ux. So now we'll calculate this and this separately. So now I'm taking the upper part, the potential energy. So because the ax is varying with x and ux we have chosen as comparison function, so ax is given by this because we have the variation of the ex like this. So here we have put the ex variation, then ux first derivative we already obtained the square of that. So we need to expand this and then multiply these two and then integrate with respect to x. So this will be lengthy integration, but only integration will be required of the polynomial, and if we do it, we'll get the expression like this for the potential energy. Similarly, for T star, the mx is varying with x, so that has been put here, and then this is the u, which we have chosen as comparison function, square of that, and then if we expand and integrate, now we will get something like this. Now we have obtained these two expressions. Now we'll substitute back in the Rayleigh's quotient. So if we substitute, this will get simplified like this. So if we take square root of this, that will be the natural frequency of the system. So now you can see that we got the natural frequency of the system for this beam, having variation in the this and this. If we would like to solve this using the eigenvalue problem formulation, then it will be just impossible to satisfy this kind of variations in the differential equations. But using this Rayleigh's energy form, we could able to get the fundamental natural frequency easily, relatively easily, because equations. In this, there's a code I have written. So actually, this is in MATLAB, but it can be written in the Scilab also. So if you see, this is symbolic manipulations are there. So this is the definition of all the symbols which we'll be using in the MATLAB. So here you can see this is the variation of the mass we are defined as given in the problem. Variation of the EA is given, which is varying with x, and this is the comparison function we have chosen. And if you want to differentiate this once with respect to x, this is the command for that. So symbolically, we can able to differentiate u1 with respect to x, and 1 represent that only one time we need to differentiate. And then the potential energy expression we obtain by, so there's an integration which we did in the previous case. Here this integration also can be done in the MATLAB or in the Scilab. So this is the function which we need to integrate, ex u1 x whole square, and then integration has to be done with respect to x. Limit is 0 to L, and then this potential energy, similarly kinetic energy, and then we can take the ratio, take the square root, all things can be done here. And you can see this is the output. So mx variation, ex variation, u1, this is the comparison function derivative of that. This is the kinetic energy terms which we got as we got previously. This one, this is the we got the from the kinetic energy, this from potential ratio, and then we can square root. So this is just code. So this will help you in you solving the assignments. If you find that the calculations are difficult, then you can use this. You can modify it according to your problem, and then or if you don't want to do it, maybe you need to do integrations recently, and then you need to get these values. So his choice is yours. Then I'll take, yeah, there's another problem which I'm not solve this. So the same variation of the same beam is there. Now we want to analyze this for the bending. Previous was for the axial vibration bending and the variation of the mass and this. So here instead of EA we'll be having EI variation because bending requires the EI terms, and the Rayleigh's quotient, potential energy, and the T star terms are here. So here I'm leaving this to you at present. So only thing will be you need to choose the UX. So UX choice is there is a comparison function you need to choose. The previous comparison function will not be valid here because here the boundary conditions are different. So here we have displacement 0 as well as the slope 0 for bending a beam case. So here displacement 0 and slope 0. Here bending moment is 0. So that means U double dot at x is equal to 0 should be there, and shear force is also 0. So U triple derivative with respect to x also should be 0. So here boundary condition requirements are more demanding. So just try out some polynomial which will satisfy the geometrical boundary condition of the cantilever beam and the natural boundary condition of the beam. As I mentioned, it should satisfy the bending and shear force here, and the displacement and the slope here. So just try out this. Just by intuition, you need to try out different polynomials, and if you can get, then maybe you can proceed to solve this particular problem. I'm leaving it to you to solve. Okay, so this is whatever we have covered. Always we got the lowest natural frequency from the Rayleigh's quotient. So is there any way by which we can able to find not only the lowest natural frequency, but maybe the second or third or fourth natural frequency depending upon our need? So this modified method that is called Rayleigh-Ritz method is the basic premise of this is similar to the Rayleigh's quotient, but because as we know that when we choose this function, the ratio gives the lowest natural frequency. If this function is equal to the first eigenfunction, then it will give to the first eigenvalue. If not, then it will give more than that. So that means what is happening is we want to minimize this Rayleigh's quotient so that we converge to the lowest natural frequency. If we somehow if we can minimize this, because the minimum value of the Rayleigh's quotient is the first eigenvalue. So here that is the thing, we will try to minimize the Rayleigh's quotient by some means so that we get the natural frequency of the system which is close to the fundamental one. So here how it does. So here we choose a family of comparison function. So in the Rayleigh's question, we use single comparison function, but here we use family. That means we need to choose different comparison functions which are independent of each other, but they should satisfy the boundary condition of the problem. So because we can have different functions which are independent of each other, but still satisfy the geometrical and the natural boundary condition of the system. So we will find out two comparison functions or three such comparison functions or four such comparison functions depending upon how much natural frequency we want to find out. So here this is the family of comparison function. UI is the family of comparison functions. So let us say if we have chosen n number of comparison functions, so we multiply that comparison function with some constant ai. A is a constant, and this is the basically the uh, actual displacement of the system, which is getting predicted from all the family of the comparison function multiplied by the unknown constant ai. So this unknown constant ai is the main key thing. So we'll try to find out ai such that the Rayleigh's quotient get minimized. So, and here one more thing is there, because we are focusing on the continuous system. If we take this n as infinity, then that will be the exact solution. But because we have truncated this to n, so that means we have neglected this constants a n plus 1, a n plus 2, up to the infinity we have equated to 0. So that is that means we should have taken the infinite series for continuous system, but we have truncated up to n. N can be 2 or 3 or 4 depending upon the accuracy required or the natural frequency, number of natural frequency required. So now the Rayleigh's quotient which we had earlier, this is again in the eigenvalue form, not in the energy form. So this you should be very careful. Whenever the L operator, or this should be M operator, whenever the L operator, M operator is there, that is related with the eigenvalue of the problem. Even the integration is there, but still this is not in the energy form. So this L operator and operator, and this is the more general definition of the Rayleigh's quotient, in which L operator can be for two-dimensional also, three-dimensional also, axial rod case or vibration of beam, in any case. So we are defining this this integration as n, which is function of Wn, and this we are defining as d. So basically denominator d and numerator n. So numerator terms I'm saying n, which is function of Wn, and denominator is Wn. So n according to that is this, and d is this. Just wait a minute. So yeah. So now, as I mentioned earlier, we'll minimize the Rayleigh's quotient with respect to these coefficients. So we are trying to find out the coefficients so that the Rayleigh's quotient get, because A is unknown. So we want to find out A such that the Rayleigh's quotient is minimized. So derivative of that we are equal to 0. Now because this is the simple derivative of the fraction, that is previous expression, this simple mathematics. So d derivative of n with respect to a, then n minus n derivative of d with respect to a, and the denominator square. So this is simple derivation which we do in the mathematics. Now this is equal to 0. That means we are minimizing the Rayleigh's quotient with this condition. So whatever the value of a will get from this expression will minimize the Rayleigh's quotient. And we have seen that if we minimize the Rayleigh's quotient, we will get the eigenvalue close to the actual one. So now this expression is simplified. This will give us this if we divide by dn. So we got this expression from the previous one. So now what we are defining key, because from here whatever the Rayleigh's quotient will get will be the minimum. So I'm defining the minimum of the Rayleigh's quotient, which is n by d, as this notation. So it's similar to the lambda, which is eigenvalue, but here I've defined the inverted v just to distinguish from the eigenvalue, which is exact value. So this inverted v is representing the eigenvalue, approximate eigenvalue, I should say. So this ratio, anyway, we know that the Rayleigh's quotient gives the eigenvalue, so that is the same expression, but this is a approximate eigenvalue. So this term I am introducing here. So this is as it is minus this ratio is the approximate eigenvalue, which is minimized according to this criteria, and this is same as this. Here j can take from 1 to n value. Yeah. So now I'm defining this. So we are introducing the kxy as this and mij as this. This will be used in the previous definitions. So here we know that kij, because of the self-adjointness operation of the L and M, kij will be equal to kji and mij will be mji. So the n which we defined earlier was this. Okay, at the very first slide when we started with the Rayleigh-Ritz method, we defined L numerator part as this. Now we are substituting the W, which we have chosen as a series combination of the comparison function multiplied by the constant. So this is the term which is representing the Wn, the comparison function multiplied by the constant and integration, the summation. Then L operator, and then Wn again the same term. The Wn is given like this. So I replaced the Wn with this series of the comparison function. And now I'm changing the position of the summation outside and bringing the integration outside. So these are constant, they will come out from the integration a and aj. The remaining terms which are function of domain x or whatever the function, they will be inside. So this term is defined here as kij. So this I am writing as kij ai this. Similarly, when we take the d denominator of the Rayleigh's quotient, substitute this Wn, M operator and Wn, which we assumed in the series form, and again we reshuffle the summation outside and integration inside. So this term which we define is Mij, this expression. So the numerator and denominator we got in this form. Now because if we go back here in the final, after the minimization of the residue or Rayleigh's quotient, we had the derivative of the n with respect to aj and derivative of the d with respect to aj. So this we are finding next. So this is the derivative of the n with respect to AR, we are doing it. So because in the n we have AI and AJ, so two terms are there. So we need to differentiate this once and this in the second time. So this is a multiplication of two quantity we need to differentiate. So this has been done here. So when we are differentiating this with respect to AR, so first it will be differentiating AI, then the AJ. So two terms will get. But now what is AI by AI differentiated by AR? So all the terms will be 0 only when I is equal to R will be 1. When I is equal to AR, then that will be 1. Otherwise, all will be 0. That means this can be written as a canonical delta IR. So when I is equal to R, this is equal to 1. Otherwise, it will be 0. So similarly here, this will be the canonical delta Rj. So when j is equal to R, then only it will be 1. Otherwise, it's 0. Now, because this Kij and Ij is symmetric, so yeah, so basically you can see that when this quantity, this is 1, then the terms will be non-vanishing, other terms will be vanishing. So now you can see when the I is equal to R, in the K we have R, J, this is the change. So then this becomes 1 and rest of the terms are 0. So this expression reduces to this expression reduces to this, and because this there n number of terms, and if you add them they will be equal. So I'm writing one of the term and twice of that because of the symmetry of the Kij. So this is the differentiation of the n. Similarly, the differentiation of the d will give us on the similar lines twice of the this quantity. Only change will be the m instead of the k, because this is the potential energy, this is the kinetic energy term, so that will be the change. Now if we go back to this expression which we got from minimizing the residual, the Rayleigh's quotient. So this is given by this, and this is given by this. So this now we have substituted in place of this here and in place of this here. Summation is outside. Aj is common. So now this expression, if you see, we encountered previously, this can be written in a matrix form like this. K, which contain all the stiffness coefficients, and A is the constant, which we have n in number. So basically, if you see, these are n such equations are there, simultaneous equations, which we are putting in a matrix form. And this is the lambda approximate value of the eigenvalue mass matrix A. So if you see, we are getting we started with the continuous system, and we got a eigenvalue problem of the discrete system. So if you remember, this is the eigenvalue problem of the discrete system of n degree of freedom system. So with this approximate the Rayleigh's method, when we discretize the continuous system to n degree of freedom system, we got the eigenvalue problem equivalent to that. Okay, so I'll stop here because then I need to discuss more on that. But this point is very important, that we started with the continuous system, this continuous system, and when we minimize the coefficients of this comparison function, the family of comparison function, we got the simultaneous equations which can be written in a eigenvalue problem of the discrete system. So that will give us n number of eigenvalues and associated coefficients, and that then can be used for finding the natural frequency, and those coefficients can be put here to get the shape of the vibrations corresponding to different eigenvalue. So I'll stop here. And if you have questions or any questions on this, maybe you can ask. So today we extended the Rayleigh method, using the Rayleigh-Ritz method for the finding the more number of natural frequency. And when we take up some more examples on this, then things will be more clear. So if you have any questions on this, please. Okay. So I'm stopping the video.